solid object that it would create if it swung through? All right, I'll have some better animations with my computer that I can show you when it's time. But a natural question would be, all right, we've got this three-dimensional solid. What is its volume, right? What's the volume of that solid? We'll be able to answer that. And it turns out that you can do that for pretty much any region. And we don't even have to wrap it around the x-axis, we can wrap it around the y-axis. So imagine me wrapping that around the y-axis. Wouldn't that look a lot different if I wrapped it around the y-axis? I think I'd have a really hard time drawing this. A really hard time drawing it. I think it would do something like this. I don't know if y'all can see that, but around the y-axis, which would be down the center, we would be able to kind of put our hand down the center of the object because it would come around like this. So it would have a hole in the middle. That's going to have a different volume than this one would. So the question would be, what's the volume? All right, so we do that. We do applications. We do some centers of mass, moments of inertia. If we have a chance, I'll do hydrostatic pressure. And we do all, get through this. This is probably a third, maybe a little less than a third, maybe like a quarter of the class. And then we get to the big chapter, which is, anyone know? No? Series. All right, series is a big deal. And I'm going to say this is about a third of the class. Now, we actually don't start series until March 30th. But we spend 1, 2, 3, 4, 5 weeks, about 5 weeks on series. And so what is a series? It's hard to kind of show you what a series is now, but let me just try and explain it to you. If you had your calculator right now and you do e squared on your calculator, which I'll do real quick. Let's see here. E squared. You're going to get approximately 7.389056099. And my calculator stops, not because that's the end of it. It keeps going forever. But at some point, our calculators have to actually stop, right? They're finite calculations here. Or we could say finite precision, all right? Now, what just happened when you typed in e squared to your calculator? What did it do? And same thing with like sine. If you did sine of 2, let's say you're in radian mode, and I type in sine of 2. Am I in radian mode? I thought I grabbed my calculator, but this is apparently not mine. If I do sine of 2 in radian mode, I get approximately 0.9092974 So what just happened? What actually happened in this machine, right? Did you say something? It's some algorithm, right? It's doing something, but what is it doing? So where are my computer science majors? That's it? 1, 2, 3, 4? Okay. So what was discovered by mathematicians, there's a very famous theorem called the Wirestrauss approximation theorem. And what it says is that if you give me a continuous function, all right, which the e to the x and sine x are both continuous functions, then there's a way to approximate that function with what we call a power series, which is going to fall into this section of the course. And we can approximate e to the x and sine of x in any continuous function as closely as we want to. Because we know an approximation is not exact, right? It's not perfect. Yeah? It's not perfect, but it's close. And the theorem says that we can get it as close as we ever want it to be. And so for many applications, it's good enough. So we study series, and what we'll realize or learn is that e to the x is actually, you probably have never seen this before, is actually 1 plus x squared over 2 plus x cubed over 3 times 2 plus x to the 4th over 4 times 3 times 2 plus x to the 5th over 5 times 4 times 3 times 2 plus ... forever. And this is what we call a power series. It's an infinite expansion of power functions. Right? Aren't these all powers of x? Right? And imagine that pattern continues forever. Then if you could continue it forever, that's exactly what e to the x is. And if you don't believe me, just plug 2 in for x. So if I use that right there and I do e squared, that should be 1 plus what? 2 plus 2 squared, 4 over 2, which I'll just leave it as 4 over 2. It's 2, but next one would be 2 cubed, 8, over, this is 3 times 2, not 0.2. So 6 plus the next one, 2 to the 4th, 16 over, what's 4 times 3 times 2? 24. I know these reduce, okay? I'm just putting it here, right? Next one, 32 over, what's this? Is it 120? Plus ... And if you get on your calculator and you actually type this in, 1 plus 2 plus 4 over 2, that's, this right here already is what, 5? And then you do plus this, plus this, plus this. I bet that it's close to this. And the further out you go, the closer you are to this. And that's exactly what your calculator did. It used that to evaluate this function. And sine has a power series, and cosine has a power series, and all your common functions have power series. But to get to that point, we need to spend a lot of time on it first. All right, so that's going to be a big chunk of the class. I'll show you something kind of cool with this. Kind of getting ahead of myself here, but what's the derivative of e to the x? Itself, right? So just take a look at this right here. If I ask you to take the derivative of this up here, the derivative of this, just if you believe that this is true, then what would the derivative of this be? Well, 0 plus what? 1 plus, okay, what would happen here? This 2 down here is really like a 1/2 x squared, isn't it? Right? So the 2 would come out, half of 2 is 1, and that'd be x to the first power. So this is just what? X plus, now this one, the 3 would pop out, right? And cancel with that 3 down there. So what would you have? X squared over 2 plus, what about the next one? 4 would pop out, cancel with the 4. You would have x cubed over, the 3 times 2 would still be there, right? So 6. Next one would be x to the 4th. The 5 canceled out, so 4 times 3 times 2. And does this look familiar? That is this, isn't it? 1x, x squared over 2, x cubed over 3 times 2. And if you kept on going, you're going to have the same thing. Kind of cool, huh? It's the only function that does that. There's no other function that does that. It's the only one. All right, so we will spend a significant amount of time on series. And in terms of difficulty, this is the way I think this course is, right? If we're going to start here, and we're going to end here, all right? We're going to graph difficulty up here, here being very hard, all right? Then I think it starts off like this. I think it goes up, comes back down a little bit, and goes up, and, well, it doesn't come down, sorry. Yeah, it just goes like that, okay? I think that's what happens. You start off in the beginning. Like the section we're going to do today in next class, these are pretty straightforward, just derivative sections. Then we start getting to techniques of integration. It's going to be pretty challenging. It's going to get harder as we go. And then when we get to applications, it kind of drops off a little bit. It's a little easier for people to, because it's really like more formulas. And so students do well on that. Then we get to the series and it picks up. But usually by the time you get here, all right, you've been through the grinder already, so you're a little better prepared for this end. But just be prepared for it. It's a marathon. Okay, this course is a marathon. that you have to sprint the entire marathon, all right? It's not going to let up, all right? Yes? Okay. I think that's it. Any questions about Cal 2 or want to say anything before I get started?
So I guess Cal 1 is differentiation, Cal 2 is integration, what's Cal 3?
Cal 3, the question is, Cal 1 is differentiation, Cal 2 is integration. Cal 3 is what we call multivariable calculus. So now what you're doing is you're dealing with functions where you're allowed to have more than one variable. So you can have functions where you have two inputs instead of one input. An example would be something like this. This is notation that you probably have not seen before. But instead of f of x equals something, right? We have f of x y equals something. And so now you can start giving me some values of x and values of y, and I can start giving you some outputs. But see, because you have two inputs, right, and one output, do y'all see that I would have two inputs? Let me try this. What would f of 2, 3 be? Replace x with 2 and y with 3. So you get 4 plus 9, which would be 13, right? So you had two inputs, one output. Compare that to something like this. Here, an example, you have one input, one output, right? One in, one out. So if I want to visualize this picture, I just need one axis for the input, one axis for the output, and I graph it, and it's a parabola. Okay, so I can visualize the function. In Cal 1 and Cal 2, I can visualize functions of one variable. In Cal 3, we go to functions of two variables. Now you need two axes for your input and one axis for your output, which means you've got to go to 3D, right? And so the ground is now x and y, and the output is what we call z, and what this would graph is a surface. In fact, that would actually graph what we call a paraboloid. It would be like a bowl, so it's a surface. And then you kind of blow the doors off and you say, well, what if there's 3 inputs or 4 inputs? And now you go outside of dimensions you can visualize. So it's multivariable calculus. But you do all the same things. Differentiation, integration, but now your functions have changed. Is that good enough? Okay. Most people think Cal 3 is easier than Cal 2. I don't know. Depends on you. All right, any other comments or questions?
Is your Cal 3 class face-to-face?
I do Cal 3 face-to-face. I do. Just depends. I haven't done it in a while. I'll probably do it in the summer if I get a chance. Yes?
Calculator?
Okay, so I go over this in the syllabus. My formal policy is no computer algebra systems. So that means TI-89, TI-Nspire, CAS are not allowed, but that's mostly because of my internet students. If you already own a computer algebra system calculator, I'm not saying to go invest in another one, but when I grade your test, I'm looking for process and procedure. I'm not looking that you got the answer right. I'm looking that you did the work. So, do you have a computer algebra system? You do? Okay.
Well, I took Cal 1 at Lakeview with
Okay.
Colonel Jack Eldridge, and
Okay.
he said I can use the calculator, but I do have to show my work.
Yeah, I'm kind of the same place here. I'll say it's okay, but what I'll do is I'm gonna walk around at the test and I'll see who has the computer algebra systems. I'll probably mark your test just so I know to pay close attention to. Is that all like complete gibberish followed by the correct answer? Or is it like good work, you know? I see, when I was in school, the TI-89 had just kind of come out, and I got the calculator, and actually I was past calculus already, so it didn't help me, but I learned to use it as a tool to help check my work and to make me kind of feel more confident. I never used it as a crutch, and I just don't want people to use it as a crutch. Which leads me to one last little conversation we should have here, and that's why it is that you're sitting in this class learning about all these, things. So What do you think? You think you're going to be out there in the workplace in 5 years, 6 years, 10 years? You're going to be sitting there working on some project, and they're going to come in there and like throw this integral at you and be like, "We need this integrated right away." You think so? Probably not. And if they did, what would you do?
Check it with the computer.
Probably go to Wolfram Alpha, and you'd probably integrate it that way. Or there would be some software that you're using, and you would trust the computer, right? So it's not about you being able to do this. It's something else. So what do you think?
Critical thinking.
Critical thinking? Problem solving?
Analysis.
Yeah, I mean, this is about the way your brain works, okay? The field that you've chosen, if you're in this class, you're probably in some STEM major, unless you're biology. So where am I, biology? I mean, we still consider that STEM, but are you pre-med or just pre-med? Anyone else, biology or chemistry also? Okay, so I know for like biology majors, the real reason that Cal 2 is a requirement is because they're weeding out the pool of people who want to go to med school. So that's just the way it is, all right? You got to suffer through this because that's the way it is. And but for everyone else, you're in computer science, electrical engineering, mechanical engineering, math, whatever it is that your major is. This is about critical thinking. This is about creating problem solvers. And whether or not you face an obstacle and you have that desire to get over it, that reward at the other side of it, getting it right, is enough to make you keep going. Because I can say from experience, Cal 1, you can do really well in Cal 1 to the point that you're a little bit overconfident. And Cal 2 is going to challenge you. I have yet to meet someone in Cal 2 that it just was a complete natural, that didn't have to learn by doing repetition. All right? It's just not one of those things that you can just watch me do some problems and then you're ready. You can take a test. So if you've never been challenged in math, this class is probably going to do that for you. And so are you going to embrace that challenge and want to get through it, or are you going to just get defeated and kind of shrivel up in the fetal position, and what are you going to do? Because the employer, that degree is supposed to mean something, right? That degree is supposed to mean that you aren't that type of person that's going to go into the corner and cry about it. I don't know, should I say that? Okay. But you know what I'm saying? We want people. My brother works for an electrical engineering company in Austin, and we talk a lot about the types of employees that they bring in. And every one of them, no matter if it's computer science or electrical engineering or mechanical engineering, no matter what the degree is, they're all problem solvers, because that's what they have to do. They have to go in there. There's no book that they can check the back for their solution, but they all feel confident in their ability to solve problems. And they all enjoy the problem and the actual journey of getting through it. So that's what we're trying to create here. Hard workers, good work ethic. All right, hopefully that's what you're ready to do. Yeah? Okay. Remember, I'm only the messenger here. I am here to give you and deliver to you the message of Calculus 2. This is hundreds of years old. All right? I'm not trying to make this difficult for you. This is what it is. All right? And we just have to learn it. I always try and remind students that we're trying to cram hundreds of years of mathematical discovery into like 16 weeks, right? So, I mean, it's a lot of information. And we'll start with 3.5. Okay, so these notes, like I said, are on Canvas. I have notes up through 7.1 or 7.2. I'm going to maybe work on completing my notes this semester. I don't have the whole semester. And it's not because I don't want to and I'm lazy. It's just because once we get to about 7.2, there's not a whole lot that I need to put on paper. It's just like, here's a formula or here's an idea and let's just see what kind of problems we can do. So the notes would be pretty minimal, but I feel incomplete right now, so I need to finish it up. But for now, we have notes at least to get us through chapter 7. Yes? Recording these? Okay. No, these are for the students who've had me for Cal 1. I don't have course videos that you watched before. Now, what I will say is that if you want to ever get a jump start on what I'm going to do, I've recorded my lectures for Cal 2 for the past year and a half, I think. So I have at least 4 other semesters of Cal 2 videos that I've already put out there on YouTube. So if you just go to my channel and you go through my playlist, You could theoretically watch the entire semester's worth of lectures with me going through these same notes if you wanted to kind of get ahead.